Okay, guys, so here's part two. I had actually made the entire video, including the second page, and then found out that when it switched to the second video, it was too big. It didn't save any of it, so yikes. I had to pick up where the first one left off, so sorry about this. In any case, so we were talking about the fact that even though this is the same acceleration increment, here it's causing the velocity to decrease. Here it's causing the velocity to increase. You decrease to stop right here, zero velocity. You turned around, and I added that in. We turned around, and now we're accelerating in the negative direction. We're increasing because we're adding negative increments to a negative velocity so it gets bigger. Right here, let's write down what C and D are now. So for C, you have a decreasing velocity in the positive direction. You're still moving forward because you're with the positive velocities. And you're doing it uniformly with negatively directed acceleration increments, okay? Negative acceleration increments, positive velocity, the velocity gets smaller, okay? So notice, opposite signs, you decrease the velocity. Same signs, you increase the velocity, okay? Now let's look at D. On D, we have increasing velocity in the negative direction because we have a uniform, that means straight line, uniform, negatively directed acceleration increment. So increasing velocity, negative direction, because we have a uniform negative acceleration increment. Notice again, same sign, increasing velocity, same sign, increasing velocity. Okay? Now, let's talk about E real quick. On E, there is no slope, so is the object at rest? No, we're moving at -8 meters per second. So of course we're not at rest. We're at constant velocity, and we're moving in the negative direction as we do it. Okay? Constant velocity, negative direction, but no acceleration because there's no slope. We're not changing the velocity. Last section, F, and I went ahead and found the slope for us so I wouldn't have to try to figure it out. So right here, from 18 to 21 seconds, we're starting at -8, and then it goes to -6, -4, -2, 0. So you're decreasing your velocity as you travel in the negative direction. See those negative signs? That means the negative direction. Why is it decreasing? Because you're adding positive increments to a negative velocity. Opposite signs decrease the velocity. All right? So right here, we're decreasing velocity in the negative direction because we have a uniform, positively directed acceleration. Opposite signs decrease velocity. Opposite signs decrease velocity. Okay? All right. Now, let's look at some common sketches of velocity time graphs so that you can see some of the different things that we can see on a velocity time graph, although we have seen most of it up there. Can you show an object traveling at constant velocity with no acceleration? Of course, it has to be a zero slope line. Since the slope is the acceleration, zero slope, zero acceleration, the velocity stays constant. You can have a positive velocity that stays constant. You can have a negative velocity that stays constant. You can have no velocity, and this is the only place where you would have an object at rest. Now remember, up here there were 3 points, 0, 12 seconds, 21 seconds. The object had 1 point in time at each of these where it was at rest, where it had zero velocity because it was on the x-axis, which is 0 for the y-axis, isn't it? Okay, so if you need to pause and copy that down, go ahead and do that. All right, now let's take a look at what happens if we want to look at an object that is accelerating. Now, I want you to notice uniform acceleration at that. I want you to notice I have 2 axes. That's because you can accelerate in two different directions and you can decelerate in two different directions. That's 4 options. So I decided to do it on 2 different axes so it wasn't so busy, okay? Let's talk about acceleration real quick. If your velocity is increasing, how do we show that? Well, again, if you're moving in the positive direction and you want to increase your velocity, you have to have an acceleration increment with the same sign. That would be a positive acceleration, and it would have to be a positive slope. So here it is. Uniform slope, constant slope, uniform acceleration. So M equals uniform positive acceleration. Okay? Can you increase your velocity? Can you accelerate in the negative direction? Sure. You start with a smaller velocity and it gets larger in the negative direction. Again, here the slope is a uniform negative acceleration. Because you add a negative to a negative, your negative gets bigger. Add a positive to a positive, your positive gets bigger. Get it? So right here, you have increasing velocity when the signs for V and A are the same. Okay? Now let's talk about deceleration. How can we show that in both directions? Well, let's look. When you decelerate, you start with a bigger velocity, you get a smaller velocity. So if you want to be moving in the positive direction, you have to start with a bigger positive velocity and go to a smaller positive velocity. So it would be a straight line that looks like this. You have a constant slope, so it's a uniform acceleration, but it is a uniform negatively directed acceleration because it's a negative slope. Now think about that. Positive velocity plus a negative increment. You're going to get a smaller and smaller velocity, aren't you? Can you do the same thing in the negative direction? Of course. You start with a bigger negative velocity and you go to a smaller negative velocity down here somewhere. So you have a uniform slope, but it has a positive sign. It's a positive slope. So add a positive to a negative, your negative gets smaller. Starting to get the idea? I hope so. So here, when you have decreasing velocity, it's because the signs for the acceleration and the velocity are opposites. Okay? Same sign, you accelerate. Your velocity gets bigger. It increases. Opposite signs, you're decelerating. Your velocity is getting smaller. Okay? Now, what about an object that has a non-uniform acceleration? A uniform where the an acceleration where the increments change value. They're not constantly the same value. All right? Well, in such a case, since the slope is the acceleration and the acceleration is changing, the slope must be changing. So you might get a curve of some kind. All right? So a changing slope equals a changing or non-uniform acceleration increment. Okay? Fortunately, since that requires calculus to integrate across a curve, and this is not a calculus-based course, we don't have to worry about that too much. But you should recognize that if the slope is changing, the acceleration increment is changing. Your values that you're adding and subtracting are different from one point to the next. All right, now, there is one thing about an acceleration time graph that we need to talk about that is very different from a position time graph. I want to talk about the area between the graph line and the x-axis. Now, on a position time graph, the area has no meaning at all. It physically has no meaning, but it does for a velocity time graph. So let's see. Suppose you had an object that increased velocity to some point, and then maybe it stayed constant, okay? And we want to look at some point in time, all right? Now, this area between the graph line and the x-axis has physical meaning. In fact, if you'll look, that's marked off by sort of a quadrilateral shape, maybe a weird rhomboidal shape of some kind, but we can actually separate this into two different little areas, a triangle and maybe a rectangle right here, okay? Those areas, when added together, give us some information. So let's take a look at one of the areas, and I'm going to choose the rectangle. We know how to find the area of a triangle and a rectangle both, but I only want to do one of these. So let's look at the rectangle right here. Okay? If we look at this side of the rectangle, it represents a change in time from this point to this point, a change in time, right? So that's one side of the rectangle. Here's the other side of the rectangle. It's the change in velocity from 0 to whatever that is. All right? So we have the two sides, and we know to find the area of a rectangle, all we have to do is take the length and the width and multiply. But what does that give us? Well, look at the units. If we say one side's the length and one side's the width, and then look at the units, velocity is measured in meters per second, time is measured in seconds, meters per second times seconds, the seconds cancel out and they leave behind meters. What do we measure in meters? Oh, we measure displacement or distance. So that is the area under the graph. How about that? We can see how far we've gone in a certain time period by finding the area. And that's kind of cool. All right? Okay. Lastly, let's take a look at a couple of examples using the formula for acceleration. We need to make sure we understand how to use it. So we're going to look at two really quick examples, all right? And I'm going to go through a very helpful process for solving problems with this, okay? First, we read the problem and determine what's the object of focus. So here it says a race car slows from 24 meters per second in the positive direction to rest in 6 seconds. What's the race car's acceleration rate? Our focus object is a race car. Okay. Now, we want to see what are the given pieces of information. Well, if you look, you can see right away, oh, here's two pieces of information, one here and one here. So we identify them. Meters per second is a velocity, but is it the initial or the final? Well, if you read the text, it says it slows from this to something else. So this must be the initial velocity. Makes sense, doesn't it? If you go from this to that, you started at the from. Now, the 6 seconds. Seconds is a measure of time, so that's pretty easy, okay? Now, the next step, once we've identified our focus object and we've identified our numerical information that's given, we have to understand one more thing. Many times in a problem, they will give you information in non-numerical form that we can convert into numerical form. I call it inferred information, okay, or understood information. So is there any inferred information in this problem that we can convert into numerical form? And yes, there is, right here. It says the car goes from this velocity to rest. That means it stopped. So that means the final velocity is 0. Now, see? So always identify the focus object, identify the numerical information, and then read carefully and identify any inferred information. Okay, that's going to be very important. Now, next step, what are we looking for? What is acceleration rate? We want the acceleration, okay? That's what we want. We want the acceleration. Right now, we only have one single equation with acceleration in it, and I kind of guess we got to use it, don't we? And that would be A equals VF minus V sub O, this is from the front, over T. Change in velocity, rate of change in velocity, final minus initial. All right, and always final minus initial. I don't care if the final velocity is smaller. We always say final minus initial. If you don't do it right, you will not come out with the correct sign for the answer. Got it? Okay. 0 is the final velocity minus 24 meters per second over 6 seconds. Notice the seconds are going to add together like we talked about on the front. And this is easy. 24 divided by 6 is 4. And we've got that minus sign right there. So negative 4 meters per second squared. Now, does it make sense there's a negative there? Yes, because we're slowing down. We're decelerating. And since the velocity is in the forward direction, the acceleration increment we're going to add needs to point the opposite direction to take away from that so you can stop. So that is correct. It makes sense. All right, so there's our answer. Now, one more, real quick. Example 2. What is the final velocity of a train which starts from rest and accelerates at 0.5 meters per second squared for 1.5 minutes? Okay, so what's the focus object here? It's a train. Numerical information. Here's one right here. What is that? Well, it accelerates at this. So this must be the acceleration. If you look at the units, meters per second squared, of course it's the acceleration. Here's another numerical piece of information. 1.5 minutes. Now, that's a measure of time, but we do have a problem. I'm sure you can see already. The acceleration is in terms of seconds. This is minutes. They're not going to work together. So before we do anything else, after we finish going through the problem here, before we start working on it, we need to convert the time from minutes to seconds so that they agree. All right, so we've identified the focus object. We've identified numerical information. Is there any inferred information? Oh, look, yes, there is. It says the train starts from rest. What does that tell us? The initial velocity is 0. How about that? Okay, so now we have 1, 2, 3 pieces of information. What are we looking for? The final velocity of the train. What is that? At the end of that time period, how fast will that train be going? Okay, well, remember, before we can start the problem, we got to take care of this little problem. The 1.5 minutes. So right here, I'm going to say T equals 1.5 minutes times, and what's our conversion factor? Well, we know there are 60 seconds in 1 minute. So I put the 60 on top and the minute on bottom so that the minutes cancel, and they'll leave us with seconds. And 60 and half of 60 is 30. 60 and 30 is 90. So that's 90 seconds. And that's what we'll use for the time instead of 1.5 minutes. Now, let's take a look at our formula. We've got A equals V sub F minus V sub O over T. But what we're looking for is this right here. Okay? We're looking for that little thing right there. So let's actually rearrange or manipulate our variables to solve for that. So here's what I'm going to do. Okay? I'm going to first multiply let's leave it right there. It's in the numerator already. Leave it there. Let's multiply over by the t. We can do that because we're dividing by it on this side, so we multiply by it on the other side. We get A times t equals V sub F minus V sub O, right? Okay. Let me do that up there. That's better, isn't it? Okay, next step. We're going to leave that right where it is. We're not going to try to move it over. We want to isolate it, so we move everything else over. Doesn't matter what side it's on. Leave it there. Now, we're subtracting V sub O. To get it to the other side, we add it. So we get AT plus V sub O equals V sub F. There we go. This is what we're going to use. That's the expression we're going to use now. So over here, we're going to say VF equals A times T. All right, well, here's the A, 0.5 meters per second squared, times the T, which, we got to use this, 90 seconds plus V sub O, ooh, but that's 0, okay? Now we just multiply. Well, notice a second cancels, so we're left with meters per second, which makes sense since we're measuring velocity. Half of 90 is 45, and that's going to be meters per second. Now notice the sign. Notice the sign. It's positive. There's no negatives here, so this is positive. So it's going to be going forward in the positive direction from rest, okay? We always assume objects are going in the forward direction unless the problem states otherwise, okay? There you go. That's about it right there. I don't think you guys will have too much trouble with the problems, with the math. It's fairly simple. I think most of you will have more trouble with the graphing. So we will be working on that, okay? Because again, people tend to want to try to interpret those velocity time graphs as if they were position time graphs. And you can't do that because what's on the y-axis is very different in each case, okay? All right, I'll talk to you guys later. Bye-bye.